Okay, I think almost on time to start the session. Hi everyone, thank you for joining the session. I am Ruben Martins. I'm a faculty here at Carnegie Mellon. I do research on verification, program synthesis, and constraint solving. And it's a pleasure to be here and sharing this session about concurrency and diagnosis. So our first talk is going to be from Martin Alfreich, and that we'll present shortly. So Martin is a PhD student at the Technical University of Munich in Germany, and he's excited here to show his work on checking qualitative liveness properties of replicated systems with stochastic scheduling. So I think we can perhaps we'll start the video.
Hello, my name is Martin Helfrich, and today I will be talking about verifying qualitative liveness properties of replicated systems with stochastic scheduling. First, let's try to understand the three main parts of the title. The first is replicated systems. A replicated system is a formal model that describes swarms of identical finite state agents. This basically means we have a set of states and a set of multi-set rewriting transitions that never change the number of agents in our system. We will have an example of such a system in a second. Please note that we never know the number of agents in our system, and thus our initial set of configurations is infinite. The next part of the title we need to understand is stochastic scheduling. With stochastic scheduling, the agents that perform the next transition are chosen in a stochastic way. This means that every transition that is enabled has a non-zero probability of occurring. By combining replicated systems and stochastic scheduling, we can model abstractions of multi-threaded programs, population protocols, and many other distributed consensus algorithms. The last part of the title we need to understand is about qualitative model checking. We are given an LTL formula where we allow Pressburger formulas as atomic prepositions to encode sets of configurations. We will have an example for such a LTL formula in a second. However, just a reminder, Pressburger formulas are first-order logic formulas over the natural numbers with addition. We are given such a property as a LTL formula, and now our task is to decide whether or not runs satisfying this property have a probability 1 in our system. Unsurprisingly, this is a very hard problem, and it's not even semi-decidable. This is why we limit ourselves to a fragment of liveness properties called stable termination properties. These have the form you see on the slides and basically mean that our system converges to a state where some post-condition holds forever. Typical properties that can be modeled as stable termination properties are leader election and consensus properties. Next, let's look at an example for a replicated system. We are looking at a flock of very cool birds that have two different colors, blue and red. The birds need to find out whether or not there are at least as many blue birds as red birds. For us as an outside observer, this is a very simple thing because we can just count how many blue and red birds there are and answer the question. However, our birds cannot see the colors of the other birds because of their glasses, and they can only interact in pairs. So, how do they do this? Well, they follow a majority voting protocol. In this replicated system, we have 4 states, blue and red for the colors, and additionally every bird can either be large or small. Whenever 2 birds interact because they're close enough, then they change their state according to the transitions on the left. If, for example, these 2 agents interact, then they change their color to small and blue. If a large bird interacts with a small bird of a different color, then it can convert the small bird to its own color, like this. If, for example, next these 2 agents interact, then we have the same thing. The large bird changes the color of the small bird to the blue color, And then, for example, these two agents could interact because remember, the next two agents are chosen in a stochastic manner. So if these two agents interact now, they become small and blue, and we are in a global state where all the agents have the same color, and the color is blue. So now they can all answer the initial question, yes, indeed, there were initially at least as many bluebirds as redbirds. We will talk about the reason for the correctness of this protocol later on. However, for now, let's look at the important property of this system. We want our birds to converge to the color of the majority. This boils down to two stable termination properties. One that tells you that if indeed there were initially more bluebirds than redbirds, then eventually there are no more redbirds left. And conversely, if we do not have at least as many bluebirds as redbirds initially, then eventually there are no more bluebirds left. Next, let's look at the replicated system model in a more formal manner. We have a finite set of states and we have a finite set of transitions that tell the birds how to interact. Then we have the concept of a configuration that tells us how many birds or agents there are in every state. Note that if you know the configuration, you know the global state of the system because all our agents are identical. If you combine configurations with the transitions, you get a step relation because if you start at a configuration, for example the one on the left, and apply a transition, you get to a new configuration, in this case the one on the right. In the paper we basically answer two questions. The first is how to verify stable termination. This is a theoretical question and leads to a sound and complete procedure that produces actual structural proof objects. The second question we answer in this paper is a more practical one: how to automatically verify stable termination. This leads to a semi-decision algorithm that is given in the paper that lets you verify properties of real-life replicated systems. So what's the idea of the paper? If you look at most stable termination proofs, these proofs are naturally structured in stages. Basically, these stages correspond to milestones where the system is getting trapped in a smaller set of configurations. This is continued until the system reaches a set of configurations or a stage where the postcondition holds. This idea leads to the concept of stage graphs. Before we can talk about stage graphs, though, we need to cover some preliminaries. First, a set of configurations S, that can be an infinite set, is called inductive if it is closed under reachability. If we look at these configurations here and their transitions between them, then, for example, this set S1 is inductive because you can never get out. The same can be said about S2 and S3. However, if you look at S4, you can see that you can get out of this set because of the red transition. Thus, this set is not inductive. Next, we have to talk about what it means for a set of configurations S to lead to another set of configurations S prime. We say S leads to S prime if every run starting at S visits S prime with probability 1. Let's look at an example. In this case, S1 leads to S2 because wherever you start in S1, you always reach S2. If we look at S2 and S3, we can also say S2 leads to S3 because wherever you start in S2, if you behave in a stochastic manner, you will always reach S3. A certificate for S leading to S prime is simply a function that assigns a non-negative value to every configuration, such that for every configuration you can reach another configuration with a smaller value. This is an example certificate for the fact that S2 leads to S3. If you pick any configuration in S2 that is not yet already in S3, then you can always reach another configuration with a smaller value. Now we can finally talk about stage graphs. A stage graph is a proof object that proves that a system satisfies some stable termination property. A stage graph is a finite directed acyclic graph where all the nodes are called stages, and these stages are inductive sets of configurations. So remember, you can never get out of a stage. Furthermore, every configuration that satisfies the precondition belongs to some stage, and if a stage has children, then we call it non-terminal, and there exists a certificate that this stage leads to its children. Furthermore, if you have a stage that does not have children, then we call it terminal, and these stages are contained in some postcondition. This means that if you are in this stage, you will continue to satisfy a specific postcondition I. Let's look at a stage graph in a more visual way to see how these 4 points interact. So this could be a stage graph. It has 3 stages, S1, S2, and S3. Remember, these stages can be infinite sets of configurations, so we can visualize them in a Venn diagram way. This could be a Venn diagram of this stage graph. For visual purposes, we picked some configurations and drew the transitions between them. The first thing we see is that all these 3 stages are inductive sets because you can never get out. This was one of the points. Furthermore, if this is the set of configurations that satisfy the precondition, then we see that all of these configurations are part of some stage. Or in other words, if your initial configuration satisfies the precondition, then you start inside of the stage graph. The next point tells us that there have to be certificates for S1 leading to S2 and for S2 leading to S3. This means that if you start somewhere in the stage graph, you will eventually reach a terminal stage, in this case S3. The last point tells us that S3 has to satisfy some postcondition. This can be seen in this case because S3 is fully enclosed by the postcondition. Altogether, this means you start inside of the stage graph. Because of the certificates, you go down the stage graph until you get stuck in a terminal stage where the postcondition holds forever. So intuitively, the stage graph gives a reason why the system satisfies a stable termination property. So let's look how this stage graph idea interacts with our example from before. Remember, we had a flock of birds. Some of them were blue, some of them were red, and we had those 4 transitions. And these transitions help the birds to decide whether or not there are initially at least as many blue birds as red birds. Remember, the system has to satisfy 2 stable termination properties. One for the case where there are indeed more blue birds than red birds, and one for the other case. For now, we will focus on just one of those properties, specifically the one where we start with at least as many blue birds as red birds and want the system to end in a state where there are no more red birds left, or in other words, where all birds are blue. A stage graph that would prove this property could look like this. This stage graph again has 3 stages. The first stage, S1, contains all the configurations that are reachable from initial configurations where there are indeed more blue birds than red birds. Because of a certificate, in this case the certificate where you only count the number of large red birds, this stage leads to S2. And in S2 there are no more large red birds left. Why is this the case? Why does S1 lead to S2? If you look at the transitions at the top, you see that whenever you fire a transition, you never create more large red birds. You only keep the number of large red birds constant, or if you fire transition T1, you reduce the number of large red birds. Thus, you will eventually reach S2, where there are no more red birds left. In the same way, S2 leads to S3 if you look at the certificate where you count the number of small red birds. If you look at the number of small red birds, the number of small red birds can only be increased by the transition T3. However, this transition can never be fired again because in S2 there are no more large red birds left. Thus, we can only fire the transitions T2 and T4. Both of them reduce the number of small red birds until we reach S3, where there are no more red birds left, and thus we satisfy the post condition. So, as you can see, this stage graph corresponds to the idea why this protocol is correct for this case. For the other stable termination property, there's a similar stage graph. We already saw the intuition behind stage graphs, and thus it is rather easy to see that there is a stage graph for a property if and only if the property holds. This is rather easy to show because our stages can be arbitrarily complicated. If we want to say something about decidability, though, we need to limit ourselves. Thus, we introduce Pressburger stage graphs where the stages and certificates have Pressburger formulas that characterize them. Showing soundness and completeness for Pressburger stage graphs is a lot harder, but still possible. If we limit ourselves to Pressburger stage graphs, then we get two benefits. One of them is that we can easily check Pressburger stage graphs, because checking such a stage graph reduces to checking a Pressburger formula. Furthermore, we also get a decidability algorithm because we can run two semi-decision algorithms at once. One is for non-correctness, and it enumerates all configurations and checks the property for this specific configuration. The other semi-decision algorithm for correctness enumerates all Pressburger stage graphs and checks if they prove the property. This algorithm does not help us too much in practice because stage graphs might have non-elementary size and thus be very huge. The natural question now is, how can this theoretical concept of stage graphs help us in practice if we want to automatically verify stable termination? Although most systems in practice have very small stage graphs, we cannot simply enumerate all Pressburger stage graphs. This is not feasible. However, if you look at most systems in the literature, you see that they make progress by killing transitions. A transition is killed or becomes dead if it can never be enabled again. By knowing this, we can limit ourselves to looking for stages that correspond to more dead transitions. This simple idea leads to a SMT-based semi-algorithm that automatically constructs Pressburger stage graphs. There are 2 points I want to make about this algorithm. First of all, it over-approximates reachability because reachability is tower hard and not Pressburger. Furthermore, the algorithm uses heuristics to find eventually dead transitions. We limit ourselves to linear ranking functions because these can show most properties from the literature. Note that this is a semi-algorithm and can fail. However, it works for many problems from the literature. For example, these are a set of population protocols where a set of agents interact and try to compute a predicate. Some of these population protocols have never been automatically verified. Please note that this algorithm not only works for population protocols or a specific system, it also works, for example, for leader election algorithms. Thank you for your attention. If you're interested in the paper, have a closer look or ask any questions by contacting one of the authors.
Thank you, Martin, for the video and the talk, and I think it was really nice. Nice animations and a really nice application of stage graphs, I think.
Thank you.
So if people have questions, we still have some time for questions. You can post them on Slack, and then I'll read them and I'll direct them to Martin. In the meantime, while people are thinking, and I know this is the first section talk of the day, so there's always a slow start. I did have some questions about the application of the stage graph, so and like in terms of like the scalability, I guess, of the approaches that you were doing. I did notice. So how many, like, what is the size in terms of nodes of the stage graphs that you're considering in the paper?
So it depends on the system. There are easier ones and harder ones. However, we usually get to the limit of the approach when we come to dozens of states and a few thousand of transitions. Then we hit the limits. That's when the SMT solver that does the work comes to the limits because the constraints are too large.
Okay. Yeah, okay, I did notice there was like a large range of times, right, where you had very easy ones, and then you quickly would go for like more than 3,000 seconds.
Yes,
All
yes.
this, yeah, the exponential behavior is well reflected there, right?
Yes, yes. However, please note that for example, for the population protocols you just saw, the number of agents that interact is unbounded, right? So we have an infinite set of initial configurations, and for each of them, the stage graphs proves that the protocol works. Like it doesn't matter if there are 10 or 1,000, it still works. So this is a huge benefit. However, for sure, if you increase the protocol and the complexity of the system that the agents perform, then you will hit some limit.
Right. Can I ask another question, I guess? What is the limitation in terms of expressivity of the current model? I mean, like, because you can only support some of this majority protocols. I guess you did say that you can also do like leader election, right? Is there any restrictions in terms of what you can actually model with your approach?
So the stable termination properties that we check have a very natural limit you can express. However, you can often take any LCL formula and perform a kind of product construction with your system, with your replicated system, and then you can apply the approach as well. However, then you easily get into territories where the system gets too complicated. However, there are a bunch of things we can do. For example, we also apply the approach in the paper for mutex algorithms, where we can show that a specific process in the system is live. This is a different thing we tried. So you can see there's a bunch of things we can apply this algorithm to.
Awesome. Well, I'm looking forward for maybe next editions to get more applications of this approach. I think it actually has some potential, and we will
work on it.
Next talk. Yeah, good job.
Thank you.
Continue working. Yeah, if people want to talk with him later on, I mean, I think he'll be around on Slack, and you can contact him.
For sure.
Thank you. Next, we'll have Daniel Schmel from Haken University. So Daniel is actually on his last year of his PhD, and he's going to be on the job market. So if you think his work is really cool, feel free to contact him and see if he's interested in a position in your place. He also has a really nice teaser video. So if you didn't watch the 1 minute teaser video, I really enjoyed the teaser videos this year. And I think Daniel's in particular was really catch my eye. So feel free to watch it. So I'll let the talk now start, and then Daniel will answer questions.
Hello and welcome. My name is Daniel, and I would like to talk to you about the systematic testing of real-world multi-threaded programs. The behavior of these programs depends on both their concurrent behavior and the input data provided to them. Thus, efficient and versatile techniques are needed that mitigate the state space explosion while still supporting real-world threading primitives, such as in our case POSIX. The core idea is to model context switches and input data, both as non-deterministic choices, and to represent executions as partial orders over the decisions taken for these non-deterministic choices. We iterate over all partial orders by using a quasi-optimal partial order reduction, and would then combine this partial order reduction with symbolic execution to model both thread non-determinism and data non-determinism. To make this approach become more than a pipe dream, we had to overcome a myriad of challenges, most of which we cannot cover in this presentation. We do, however, encourage you to read the extended version of our paper on arXiv and check it out for yourselves. Today we start with modeling thread signaling and symbolic choices as partial orders and explain how we use data races to keep these partial orders compact. We then describe our delta-based program state fingerprints that we use for cutoff events and how our algorithm enables heuristic exploration of the partial order representation. Let us start off with an example. Our example program has two global variables, a mutex m and a condition variable c. The first thread begins by reading input into the local variable x. For the purposes of this demonstration, reading input is a pure function without any side effects, such as locking stdin. Thread 1 then acquires the mutex m and branches upon whether the input it just read into x is less than 0. If that is the case, it waits upon the condition variable c. Waiting on a condition variable releases the associated mutex, in this case m, and suspends execution until the condition variable is signaled from another thread. At this point, the mutex is reacquired and execution continues. Finally, thread 1 releases the mutex. To make matters interesting, there is a second thread. Thread 2 begins by setting the local variable y to 1. It then acquires the mutex m and signals the condition variable c before releasing the mutex again. Our partial order has 5 categories of actions: local actions, mutex-related actions, signals, waits, and broadcasts. Broadcasts work similar to signals, but are not covered in this example. Details can be found in our paper. Let us show you how an execution of this example program is modeled as a partial order. Starting off with thread 1, the first line is a local action, which is independent of all other threads and creates event number 1. The acquisition of the mutex m in line 2 is, unsurprisingly, modeled as the acquisition of a mutex. Branching upon x is a local action again, however it is a special kind of local action, a symbolic choice. Let us assume for the moment that the input value is greater or equal to 0, and therefore the if branch cannot be entered. Thread 1 finishes execution by releasing the mutex m, which is modeled just so. Since thread 1 is finished, we have to execute thread 2 next. It starts off with a local action, causing event 5 to be independent of all other events we have explored so far. Locking the mutex m, on the other hand, depends upon it having been released by thread 1 in event 4. Next, thread 2 signals the condition variable c, but the signal is lost because no thread is waiting to be signaled. Finally, thread 2 releases m again. Now, let us reconsider the choice we made in event number 3. It is easy to see that the execution would have gone differently had we made a different assumption in event 3. Making a different choice here results in a new event 9, which starts a conflicting extension to our previous partial order. While event 2 is part of both executions, events 3 and 9 can obviously never be in the same execution. Following the execution of event 9, we now enter the if branch and begin to wait on the condition variable c. We model waiting on condition variables in 2 phases, the first of which is wait 1, which releases the mutex and suspends execution. Since thread 1 is now suspended until it receives a signal, we have to continue executing thread 2. Let us clean up the presentation a bit before doing that. Note that both appearances of event 1 are still the same event, and that events 3 and 9 are still in conflict. Now thread 2 acquires m and signals the condition variable c. Thread 1, however, can only continue execution once mutex m is released, as it will resume execution already holding m. Once that happens, thread 1 can execute the wait 2 action, which does exactly that. Finally, thread 1 releases the mutex m. Instead of letting thread 1 acquire m first, we could of course have chosen to let thread 2 do so before thread 1. Following this conflicting extension, thread 2 signals c, which is lost again, before it releases the mutex. Once the mutex is released, thread 1 can acquire m and perform the symbolic choice. Let us start by assuming that x is greater or equal to 0 again, which will lead to thread 1 releasing the mutex. Choosing x to be less than 0, however, leads to event 22, which will cause thread 1 to enter the if branch, where it begins to wait on the condition variable c. However, since the signal has already been lost and all other threads have exited, there is no way that thread 1 will ever continue execution. This means that we have just detected a deadlock. This example completely omits what happens when 2 threads mutate the same byte of global state. That is, what happens when there is a data race. Traditionally, many partial order reductions attempt to find all interleavings of data races. We, however, exploit that our source programs use the C-memory model. The C18 standard has quite a bit to say on the topic of data races, but the relevant section is really quite short. Any data race results in undefined behavior. Taking this hint, we add a data race detection, which gives 2 key benefits. Firstly, it empowers our technique to find a whole new category of bugs. And finding bugs is really why we are testing the program in the first place, after all. Second, by ensuring that memory reads and writes can never interfere with one another directly, we can specify a much more compact partial order representation that does not need to concern itself with modifications to the global state specifically. Now, since our partial order representation relies on the fact that data races cannot ever occur, since they would already have been detected, the data race detection has to be complete for the composite algorithm to be sound. We achieve this goal by building upon our happens before relationship and generalizing the trivial dynamic algorithm to the symbolic case. This way, we can always report an error to the user or correctly explore the behavior of the program. In addition to designing the partial order to be compact in the first place, we also try to remove redundancies from the exploration by implementing cutoff events. Cutoff events build upon the realization that multiple paths that lead to the same program state are redundant. To detect such multiple paths, we compute a fingerprint for each event that uniquely identifies the program state associated with said event, with high probability that is. These fingerprints must be efficiently computable and only depend upon the history of that event, meaning may not change no matter what happens concurrently. Our algorithm achieves these goals by defining the fingerprint as the bitwise exclusive OR of a strong hash of each fragment of the program state. Fragments, in turn, are just fine granular pieces of the program state. For example, we consider each byte on the heap individually, as a fragment that has the tag concrete heap byte, for bytes who have a concrete and not some symbolic representation, of course, followed by its location and actual value. Another fragment is used to store the existence of memory allocations, as alloc followed by the base address and the size of the allocation. To compute these fingerprints, we represent each individual change to a fragment, and thus the program state, as a delta. This delta is then XORed into the old fingerprint to form the new fingerprint. This is possible because the delta itself is just the bitwise exclusive OR of the hash of the old fragment and the hash of the new fragment. The old fingerprint must have contained the hash of the old fragment as well, which allows us to rewrite the formula like this, which shows that the hashes of the old fragment cancel one another out, leaving us with whatever else the old fingerprint contained, XORed with the hash of the new fragment. Consider this example partial order of 7 events. Let us start off with event 1, whose fingerprint consists of all changes that have been made so far. Since it is the only event in its history, that means all changes made in event 1 itself. Ignoring any possible initial value for the sake of clarity of the presentation, this results in its fingerprint being exactly delta 1. The fingerprint of event 2 XORs this delta 1 with the delta of event 2, delta 2. For event 3, we have to be aware that the history of event 3 only includes event 1, but not event 2. Thus, its fingerprint is delta 1 XOR delta 3. We can similarly fill out the fingerprints for events 4, 5, and 7. For the last remaining event, event 6, fingerprint computation works the same way, but requires us to recall that its history contains all events except for event 7. Therefore, its fingerprint is the XOR of all deltas, except for delta 7. Despite all these improvements, real-world programs are so complex that their analysis will still not complete. Symbolic execution tackles this by exploring the execution tree with heuristics that attempt to optimize exploration coverage such that bugs are found as early in the exploration as possible. For unfoldings, however, exploration algorithms have previously explored the search space in either a DFS or BFS manner. Since DFS exploration algorithms tend to follow a tree structure that integrates well with how symbolic execution sees the problem, we have chosen a DFS algorithm as our foundation. When this algorithm explores a node in the search tree, it will start off by fully exploring the left child tree. After that, it will try to explore the right child tree, which does not necessarily exist. Once the algorithm reaches this point of the exploration, however, a potential right child node must have been discovered before, if it exists at all. Therefore, the algorithm can conclusively decide whether a right child node exists or not, and explore it if it does. When traversing the tree in a non-DFS manner, however, the left subtree is not fully explored, which means that we cannot answer the question whether the right child node exists in general. We may, however, already have found a right child node, which then obviously exists. It is therefore always possible to answer the question conclusively if we do have a right child node. We just cannot disprove its existence until the exploration has advanced far enough to fully cover the left subtree. Our solution deals with this by storing a sweep bit. That sweep bit lets us explore the tree in an arbitrary order, but only cleans up after the nodes in a DFS order. We implemented our algorithm as a tool on top of the CLI symbolic execution engine. You can find our tool on GitHub, and please feel free to give it a spin. To evaluate its effectiveness, we asked ourselves 3 guiding questions. 1. Can our tool find bugs in multi-threaded industrial-sized benchmarks? 2. What is the resource consumption of our technique? And finally, 3. How does our technique compare to the state of the art? To answer question 3 in particular, we compared ourselves against the winner of the 2019 SVComp competition, Yoger CBMC, on both real-world and SVComp benchmarks. While your CBMC did perform better on the SVComp benchmarks, our tool did quite significantly better on the real-world benchmarks. Please find the exact results in our paper. We will now discuss how our tool did on the real-world benchmarks by answering the first two questions. The target programs for this experiment are memcached in various versions and GNU sort. Both of these have some versions indicated with plus. This plus indicates that we have added some fixes so that our analysis can get deeper into the main program. Both programs are in widespread use, and with memcached weighing in at about 31,000 lines of code and GNU sort consisting of over 86,000 lines of code, neither of them can be considered a toy program. In our configuration, they used from 1 to 10 concurrently active threads, although both programs can be configured to use as many threads as the user likes, of course. We did find several bugs and data races in both programs, but please be aware that the number of error paths is of course not equal to the number of unique bugs that we detected. Therefore, we come to the conclusion that our tool can indeed find real bugs in multi-threaded industrial-sized benchmarks. The time consumption of our tool ranged from 7 seconds to 4 hours. This has a few causes. On the low side, memcached contained a few bugs fairly early during its execution that would terminate the analysis by virtue of encountering the bug on all possible paths. On the high end, we configured a timeout of 4 hours, which some runs reach. The remaining runs run into the memory limit, which we configured to be 200 gigabytes. As can be seen from the halt reasons, our tool requires a significant amount of resources, and our earlier claim that real-world programs will consume as many resources as we can throw at them sadly holds. We would like to note that this effort pays off in the number of retired executions and the number of discovered events. In the time and memory bounds that we set, our tool required hundreds of millions to billions of instructions and discovered hundreds of thousands to millions of events in the unfolding. To conclude this talk, we have combined partial order reduction and symbolic execution to explore both thread non-determinism and data non-determinism at the same time. Our algorithms in our tool both support most of the POSIX threading primitives, including, for example, condition variables. We have found multiple bugs in memcached and GNU sort and provide many foundational and practical contributions that make our approach efficient and robust. Finally, we would like to ask you to check out our tool on GitHub and to read the extended version of our paper on archive. I promise it is worth it. We hope you enjoyed our presentation and have many interesting questions for us to answer.
Right. Thank you, Daniel, for that great talk. So if you guys have any question that you want to post on Slack or later on, you can also reach directly Daniel. In the meantime, I'll ask a question. So I noticed when you're computing fingerprints, like you're doing a lot of XORing. Would that be like an issue in terms of the scalability of the approach or even the blow up of the memory size? I don't know. Is that influencing the solving time in the interpretive way, I guess?
So we compute these fingerprints iteratively, and then we end up with a finite-sized hash. In our case, we use Blake2B for the hashing. So we end up with, if I recall correctly, 256 bits that we store for each event. Now, you may recall from unfoldings that we do actually accumulate storage that we require over the execution of our program. And that is part of the final memory cost. However, it is a comparatively low part in our experiments, at least, because the actual number of open states far outweighs the amount of hashes and done events that we store.
I see. Another question. I found it really interesting that they actually scale up to like real benchmarks, right? I mean, I think that's always a big challenge, especially when you're dealing with concurrency, right? So you did mention that there's like that the number of error paths does not actually equals the number of errors, right? That you found, right? So can you talk a bit about like how many errors you actually found on those programs and what kind of errors were they? Because I did notice when I read your paper that you did report them to the authors, right? And they were patched, some of them. Maybe you can enlighten us a bit about that.
Yeah. Most of the errors we found were in memcached. There was one bug in GNU sort that we found a bunch of different ways, but basically the thing in sort that we found was a data raise on a pointer, which on x86, 64 with GNU, GCC, and so forth, does not actually turn out to be a problem in practice. I think the worst thing that we could make it do was recompute a bit of the parallel computation. So it was in a sense a bit optimistic synchronization, but didn't cause any like user observable faults. Now, of course, that could fail a lot harder if you were to compile it for some weird architecture, but that was really it. The memcached example, however, had a few, so the 7-second front is in especially, they ran into initialization bugs. For one, there was actually a bunch of double initialization of pthread constructs, which the pthread standard considers to be undefined behavior. There were also a bunch of different data races ranging from, well, nobody really cares because we're just collecting statistics, to, well, in theory, this could crash the program. In practice, you may have heard people use memcached and they don't complain all the time that it crashes all the time. So again, this is a bit of the verification problem that we find bugs, but only the bugs which aren't really that much a problem in practice, because if they were a problem in practice, people would be complaining about them.
So I think Stefan raised his hand actually here. So maybe he has a question.
Can you just say a little bit more about the partial order reduction? For example, why is it called quasi-optimal? And how does it differ from like some of the classical partial order reduction schemes in the literature, like ample set partial order reduction or stubborn sets and that kind of thing? Or anything more about it?
Yeah, I think that's a question best answered by Caesar, who built both this partial order reduction and the partial order reduction that we actually use the foundations of.
Yeah, that's a good question. It's called quasi-optimal partial order reduction because it's not optimal. When there was this paper by Abdullah and others in Popel 14, where they presented the first optimal partial order reduction. Later, we proved that actually computing the next, you have one partial order, you need to compute the next partial order you're going to explore that requires solving an NP-complete problem. So what this quasi-optimal partial order reduction does is that you can avoid computing that NP-complete problem with a polynomial approximation of the exponential algorithm. So there is an algorithm behind it, and this is what we are applying to the symbolic execution on top of CLI. The main difference with classic partial order reduction sample sets and the original papers by Flanagan, Cottrell 2005, and so on, DPOR, is that this is essentially building on top of a partial order semantics. So it's building a prime event structure. If you want, that's the main difference. It's based on a data structure that allows you to explore, if you want, explore the state space in an optimal manner. Here we have decided not to be optimal in the sense of Abdullah Popel 2014, but we can at the cost of modifying a single function in the algorithm.
Thank you for that clarification. Maybe you guys can follow up more offline. I think this is maybe also a longer discussion probably for the details there. Okay, so coming up next, we do have Berk Shishiri so he's a PhD student, first year, if I'm not mistaken, at the Research Institute of the Foundations of Computer Science. And he's going to talk about root causing linearization violations.
Hello everyone. Today I would like to talk about our work, root causing linearizability violations. This is joint work with Konstantin Ena, Azad Efersan, and Suavron Mutluergil. Efficient multi-threaded programs are mostly based on concurrent objects, in which operations are executed in parallel. It's complicated to program these objects correctly, because of the challenge in reasoning about thread interleavings and overlappings. Linearizability is the de facto correctness criterion for the concurrent objects. If an object is linearizable, its operations can be rearranged such that they appear to be executing atomically and sequentially. Operations that are overlapping in the execution are called concurrent, and they can be ordered in an arbitrary manner. However, the order between non-overlapping operations should be preserved. Linearizability can be restored by making coarser-grained atomic actions inside operations. It can be achieved because if all of the operations bodies are atomic, then they are trivially linearizable. Nonetheless, having coarser-grained actions deteriorates the level of concurrency and the performance. To our knowledge, there are some tools to prove linearizability or identify linearizability errors for a single trace, and these tools can find out non-linearizable executions. However, they do not provide any guidelines about the root cause of a non-linearizability violation or how to tackle these errors. In this work, our main goal is to find root causes of linearizability violations in concurrent objects. We interpret root causes as atomic blocks to disable non-linearizable executions according to the coarse-grained interpretation. We will equate root causes with minimal atomic blocks, called as optimal repairs, which will surely disable non-linearizable executions. If there are numerous root causes, we need to find a heuristic to differentiate them. Our proposal is to rank them with respect to the number of good executions they disable. Let's briefly visualize how we reach our goal and identify those root causes. On the left-hand side, you will see a pseudocode for a concurrent stack, which is not linearizable. And we will try to figure out what are the root causes of these non-linearizability violations. First, I will briefly explain the pseudocode. The values pushed into the stack are stored into an array called items. A shared variable range keeps the index of first unused position in items. The push method stores the input in the array and it increments range using find and increment primitive. The pop method reads range and then traverses the array backwards starting from range -1 until it finds a position storing a non-null value. It also nullifies all the array cells encountered during this traversal. If it reaches the bottom of the array without finding non-null values, it returns null. On the right-hand side, there is an execution of a client with 3 threads executing 2 push and 2 pop operations in total. The library is not linearizable because both pop operations return the same value b, which was pushed only once. We have 2 non-atomic sections that could be interpreted as a root cause. First one is the section that includes the 2 statements in the push method. And secondly, the section containing the statements at lines 8 and 9 in pop because of the conflicts in this figure. I will explain why making these parts atomic will disable this execution in upcoming slides. In this example, the one removing less good executions is the atomic section inside pop, so it will be proposed as the best candidate for the root cause of non-linearizability violation. Basically, in this work, we proposed a method that takes a set of linearizable or non-linearizable traces and outputs a set of root causes, which are ranked by our heuristic. We implemented this algorithm and created a fast and efficient tool, which we evaluated experimentally on non-trivial libraries. We provided a proof to show that our algorithm is optimal in terms of asymptotic complexity. So before starting to go into technical details, I would like to state the plan for the rest of the talk. Since we are getting a set of traces, we are creating our models over them. We are calling these models as interval graphs. First, I will start with interval graphs. Next, I will explain how we find the root causes on these graphs. For this, we are computing critical segments, which I will describe detailedly. After that, I will talk about our algorithm to compute root causes and optimality of it. Then, we will analyze the heuristic for ranking optimal repairs. Finally, I will show the details about implementation and experimental evaluation with our observations on them. Now, let's start with the first part. Figure on the slide will illustrate an interval graph over a given trace that represents data flow and control flow dependencies in an execution. A node denotes an event, and events with the same color are from the same operations. We have 2 types of edges in this graph, which are called program order edges and conflict edges. Program order edges are from any events E1 to E2 if they are in the same thread and E1 occurs before E2. Conflict edges are from any events E1 to E2 if they are in different threads, access the same location, and at least one of them being a write such that E1 occurs before E2. We can get a decomposition of events over the interval graph. We can group these events if their operations are the same, and there should be a link between these events by program order edges. We are calling these sets of events as intervals. These intervals can have an arbitrary number of events from the same operation. For example, I1 is a non-singleton interval which contains 4 events. Edges of events can be accepted as the edges of intervals that wraps those events. As can be seen easily, we can have many decompositions even with few operations. That's why there can be many interval graphs of the same execution. If there is a cycle in an interval graph, making the intervals on the cycle atomic disables this execution, but these atomic blocks are not necessarily minimal. Also, this is not necessary because some of the intervals don't need to be atomic, or making some smaller parts of an interval can be enough. Therefore, we are looking for all the parts that you need to go by reverse program order to traverse any cycle in the graph. From these atomic blocks, we obtain the minimal ones. These minimal atomic blocks that disable a certain execution will called as critical segments. Now, we can check an example cycle. For instance, in the figure, there is a cycle shown with red arrows. Here, you can see the critical segments for a certain cycle. Atomic section sets over these critical segments are the parts that are enough to eliminate corresponding non-linearizable execution. With atomic section sets over these critical segments, like conflict serializability for databases, we are preventing non-linearizability in these executions by breaking those cycles. Now the question is, how can we find all these critical segment sets? As a naive approach for each decomposition, we can directly try to enumerate all the critical segments for each simple cycle. This algorithm is obviously very inefficient and its complexity is exponential, even with fixed number of threads. Now, I will talk about another algorithm, which is polynomial when the number of threads is fixed. Here, how it works. Rather than enumerating all decompositions, we can have an extended interval graph with reverse program order edges, as in the figure, to obtain maximum decomposition. Then we can try to find all critical segments over this graph. We can add program order edges if both events are from the same operation. So, the algorithm is reduced to finding all critical segments in a given graph. The idea behind this algorithm is that first, applying the algorithm for just this graph with maximum decomposition rather than for each decomposition is sound. Secondly, just checking simple Cortus cycles over an interval graph is enough to find all critical segments where the number of Cortus cycles in a graph is bounded with the number of threads. As a side note, a Cortus cycle is a cycle which has at most one vertex in each thread. In other words, the number of conflict edges in a Cortus cycle must be less than or equal to the number of threads. Now, let me explain these ideas. As you can see from the figure, we can find all critical segments on the extended interval graph by just checking simple Cortus cycles. Green arrows in the figure represent the cycles, and the red lines show the critical segments. You can find the related proof in our paper. We know that the conflict edge in a Cortus cycle can be at most equal to the number of threads. Otherwise, by the pigeonhole principle, at least two conflict edges end up in the same thread. That's why the number of Cortus cycles with at least one conflict edge is bounded with the number of threads. When we obtain these critical segments, we are eliminating non-minimal ones. Like in the figure, we are not proposing the critical segment in the second cycle since it is subsumed by the one in the first cycle. Interestingly, this upper bound on the number of Cortus cycles in a graph is not loose. There is a class of traces parameterized by the number of threads, such that the number of Cortus cycles with at least one conflict edge is proportional to the number of conflict edges when the number of threads is fixed. Let there be k parallel conflict edges between each consecutive thread, like in the figure. To form a cycle, one needs to pick one of k edges between each consecutive thread in all threads. Each cycle creates a different critical segment set, and all of these sets are minimal. Therefore, the number of simple Cortus cycle is equal to the number of minimal critical segment sets. As a result, we can find all critical segments in polynomial time, and the complexity is reduced where enumerating all the Cortus cycles is polynomial when the number of threads is fixed. Having an algorithm in which complexity is polynomial with a fixed number of threads is not an obstacle, since recent work shows that most linearizability violations can be caught with 2 threads only. We will propose atomic section sets over these critical segments, but after applying our algorithm, we will have at least one optimal repair and maybe more. Then, how we will select the best candidate. As I mentioned, we will rank a candidate higher among each other if it disables less linearizable executions than others. This heuristic relies on an experimental hypothesis that there are harmless cyclic dependencies that occur in linearizable executions. For instance, let's get back to the first example, which is not linearizable. Think the execution where the first two threads are interleaved, exactly as in the figure on the left-hand side, and where the pop in the third thread executes after the first two threads finished. This execution is linearizable. From the two optimal repairs, enforcing only the atomic section in the push will disable this linearizable execution. But even if we count all good executions of the same client, we will find that the number of good executions disabled by the atomic section in the push method is greater than the atomic section in the pop method. With our ranking heuristic, we counted each of these kind of disables precisely, and as expected, the atomic section in the pop, which permits this linearizable execution and also the root cause of the violation, is ranked higher. As a result, this stack is linearizable when the two statements are executed atomically. So, how did we use our algorithm? We implemented a practical tool to apply all these ideas for proposing optimal repairs to root causes. Here is the structure of our implementation. In this tool, first we are discovering clients with linearizability violations. Then, we are generating all traces of the client executions up to partial order reduction. We are creating interval graphs with maximum decomposition. Next, we are finding cycles over these graphs in non-linearizable executions to obtain all optimal repairs. Finally, we rank these repairs by checking how many good executions are being disabled with corresponding atomic sections. We discovered the clients that have non-linearizable executions by running a tool called Violat on the libraries. Violat is another tool which can be used to find clients that expose linearizability violations. We use Java Pathfinder and certain listeners of it to generate all the traces of client executions. After having these traces, we generated extended interval graphs over these traces and ran our algorithm on these interval graphs. The last two phases together are the parts that are implemented as our algorithm up to now. To test our tool, we selected our concurrent objects from a repository called Synchrobench. We know that this repository contains linearizable libraries. We considered three libraries from this repository: two linked list set implementations with coarse grain and fine grain locking respectively, and a map implementation based on an AVL tree overlapping with two single linked lists and fine grain locking. While using these libraries, we created three non-linearizable variations for each library by changing the position of particular locks in their codes to obtain non-linearizable libraries. We generated those variations by shrinking an atomic section only in the add method, only in the remove method, or an atomic section in each of these two methods. Despite this example, our approach doesn't need libraries that already have locks. Here, we can see examples of code segments from the original and modified library. We change the position of locks and shrink the atomic sections as in the example. While testing, as the root cause, we expect to obtain the atomic section on the left from the original library. So what are the results of the experiments? This table is for one of the libraries in Synchrobench. The rest of the experimental data can be found in the paper. Now, on the first column, you can see the original and modified positions of locks. In the second column, we can see the operations for specific client executions. From these operations, letter A represents add, letter R represents remove, and letter C represents contains. And the last column gives the first or the first two optimal repairs in the ranking obtained with our approach. The numbers next to arrows show the number of linearizable executions disabled after making the code segments next to them atomic. As can be observed, all the atomic sections are similar to what we expected for this library. Some results may not be as expected due to the choice of some particular clients or because of using all traces in our ranking heuristic. However, if our tool ranks a repair first for a particular client, then after repairing the library according to this repair, the corresponding client produces no linearizability violations. Bottleneck of the computation in our tool is generating traces, which is handled by Java Pathfinder, and it takes a few minutes. Here, we try to compute the ranking heuristics based on the set of all good executions. This bottleneck can be dealt with, and we can do it by compromising from completeness without enumerating all possible executions, but just a subset. This modification surely will improve the performance. For most of the clients that we experimented on, our algorithm proposes optimal repairs around 10-20 seconds after obtaining the traces from Java Pathfinder. We presented a method to compute root causes of linearizability violations for sets of traces. We show that its polynomial time when the number of tests is fixed. We did experimental evaluation on non-trivial libraries, and it worked successfully in reasonable running time. In future, we want to investigate other interpretations of root causes like order constraints. Also, we can look to other kinds of specifications like weak consistency rather than linearizability to analyze finding root causes of these specific violations.
Okay. Thank you, Burke, for that talk. If you guys have any questions, you can post it on Slack, or you can raise your hand, and I can also unmute it here, even though Slack is preferred just so that other people will also know which questions you asked later on. I do have a question, I guess. So you talk about this optimality, right? But in some sense, you do depend on the traces that this Java Pathfinder gives you, right? So what happens if your set of traces doesn't cover all the possible interleavings? Could it be possible that you actually miss the ground truth? And does this actually happens in practice or not? Can you clarify a bit about that?
The thing is, it's not possible because Java Pathfinder returns complete traces. So after obtaining them, it's just we just apply our algorithm and we know that it's complete because Java Pathfinder outputs the traces complete.
But if I would replace Java Pathfinder by some other tool or client, right, that would give me a different set of traces. So you do really depend on the completeness of the traces in some sense. Right?
Yeah, exactly. Yeah.
Okay.
But as I said, for the bottleneck, we don't need to compute. We don't need to get all the traces. So it will increase the performance, but as I said, it will decrease the completeness. So yeah.
Yeah, I guess there's always a trade-off there, right?
Yeah.
Because I was also looking at your instances, and they were ranging between 100 and 1,000 lines of code, right? And you were saying that the bottleneck is still the symbolic execution engine, if I understand correctly from the approach, right? So do you think by losing, I guess you don't want to lose completeness in the sense that, of course you don't want to lose that, but do you try to have this trade-off where you may have less traces or less information and try to scale more and see if it's possible to still be have very good results or not?
No, we didn't try it because the algorithm is actually took 10 to 20 seconds for the libraries that we tested. So we didn't need to give any, we didn't need to get rid of completeness, but we could apply it on all traces in 10 to 20 seconds. So we didn't need to do that. But maybe for complex libraries or maybe libraries that are implemented in low level, it will be a better solution to decrease this bottleneck. Yeah.
Well, thank you, Burke, for your answers, and thank you for the great talk as well. Okay, coming up next, we have Orna Grunberg. She's a professor at Technion, and she's going to talk about misfault localization for problem repair. So I'll give you the talk.
My name is Orna Grunberg, and I will talk about masked fault localization for program repair. This is a joint work with Batchen Rothenberg. Automated program repair receives a buggy program. It does some changes to the program to some location in the code and result in a patch program which is correct. This mission must be quite heavy because there are many locations in the program to choose from, and thus the repair may may go through many iterations until it hits a correct program. Fault localization might be in help for the user that repaired the program. Fault localization, its goal is to focus the programmer attention to locations that might be relevant for the bug. So here we are again with a buggy program and violating run. And fault localization will point to a set of locations that are suspicious that might be relevant for the bug, repair will choose one of more of these locations, will repair them, and will result in a correct program. As said, fault localization should focus the programmer's attention on locations that are relevant to the bug. If it is not precise, however, then when it is too restrictive, it might miss a potential repair, while if it is too permissive, it will cause an extra search work. Most of the fault localization algorithms in the literature return a set of locations that may be relevant. There is no guarantee that all returned locations are relevant, nor that every relevant location is returned. We suggest a novel notion of must fault localization. Before presenting this notion, we need to present another one, which is repair scheme. Repair scheme identifies the changes to program statement that are allowed by the repair. So for instance, repair scheme that we will refer to in this talk is smute, mute for mutations, that allows syntactic replacement of operators on the right-hand side of assignment and in conditions. For example, we can replace a plus by a minus, greater than by a smaller than, constant C with a constant C plus 1, and so on. So a must fault localization algorithm is an algorithm that for every buggy program and for every bug returns a must location set, and the must location set contains at least one location from any successful repair of the bug. This means that it is impossible to fix the bug without using locations are in this set. Or in other words, any repair must consist at least one location from this set. It turns out that must location set depends on the chosen repair scheme. It can be shown that a location set might be must for one repair scheme and non-must for another. In this work, we develop a fault localization algorithm. We prove that it is must with respect to smute. We implemented it within the repair tool or repair and show a significant speed up. Our setting is formal automated program repair, which means that we do not get a set of tests to identify bad behaviors from good behaviors, but rather we get a specification, and we require that the program will meet the specification for all input. In other words, it should pass formal verification, and we consider bounded verification. So in addition, we consider search-based program repair. We are given, as before, a buggy program and a patch. Possible patch are according to the repair scheme, and the search space are all possible patch programs. Now we go in rounds of generate and validate. We generate one of the program from the search space, and if it's correct, then it goes to the user, and if it's incorrect, it's just thrown away. We will explain the algorithm for must fault localization by example. So here is a buggy program, and we can see a buggy run by starting from x equals 0 and w equals 0, then t becomes 0, y becomes minus 3, z becomes 3, and now when we get to the if, w is not greater than 3, and therefore we go straight away to the assertion, and the assertion is violated because at this point y is minus 3 and z is 3, and it doesn't hold that minus 3 is greater than 3. So here is a buggy run, and in order to build the must location set, we will first translate the program into a program formula in the form of single static assignment, SSA. And this is done by indexing each of the occurrences of the variables and also adding a Boolean variable for each condition on any if or while. So for instance here, the if w greater than 3, then and so on, is replaced by G0 that gets the value W0 greater than 3, and then all the rest of the computations are, depend on the value of G0. We see that in addition to the set of constraints representing the behavior of the program, we also have a constraint that negate the assertions and just add them to the program. So now if we get a satisfying assignment, this assignment represents a behavior of the program that does not satisfy the assertion, meaning a violating run of the program. So in order to compute the fault localization, we compute a dependency graph between the variables in the program, and we start by building a static dependency graph between the indexed variables coming from the constraint set. So for instance, y2 has an arrow to y0 because the value of y2 depends on the value of y0 if g0 is false, and on y1 if g0 is true. All edges that are not marked the conditions there are just true. But we are not interested in this dependency graph in general, but in its part with respect to the specific bug that we have. In this specific bug, G0 is false, and here we see that the value of y2 in the bug depends on all the blue variables in the dependency graph. And this is the slice of y2. So now we are going to compute the slice of y2 and also the slice of z0, because these are the two variables that are part of the assertion that was violated. And we get a set of constraints that determine the value of these two variables. And now we extract from this set of constraints a set of statement from the original program. And this is the must fault location set. We implemented the must fault localization within the all repair tool, where all repair is based on generate validate, and it returns all minimal repairs from the search space based on the repair scheme as mute. The minimality is with respect to the number of changes, we call them mutation, applied to the code. So here is how all repair works. It generates a program, and if it is correct, it doesn't only eliminate this specific program from the search space, but also eliminating all other programs that use a non-minimal set of mutations. But if the generated program is incorrect, then no pruning is applied. So we want to make all repair more efficient and to further reduce the state space, and to reduce it both when the mutated program is correct and when it is buggy. So when it is correct, we know what to do. We just eliminate all the non-minimal mutated program that relate to this specific mutated program that we got. When it is when the mutated program is buggy, then what we do, we compute the mask location set F for the bug in the mutated program PM. We remember that F is a set of statements that guarantees that the bug is there if it is not changed. And therefore, we just eliminate from the search space all mutated program containing F because they also contain the same bug as PM. So here it is. We now generate a program. It is buggy, and now we prune the search space, and we eliminate all programs that have the same mass location set. And as before, when we get a correct patch program, then we prune the search space according to minimality. We have the theorem that says that the new algorithm, fault localization all repair, is sound and complete, meaning that we do not miss any bug, any repair, any successful repair by pruning the search space. We experiment with the new algorithm and compare it with all repair. We have two types of benchmarks. One is TCAS, Traffic Collision Avoidance System for Aircraft. The other one is CodeFlow, which is a set of solutions submitted by programmers to the programming contest as in the site CodeForce. Technically, it is interesting to note that TCAS doesn't contain any loop, and CodeFlow has some of the solutions have loops, and in that case, because we are interested only in bounded verification, we unwind the loop for 2 or 5 or 8 or 10 times. The specification that we use is checking equivalence to a correct version. So altogether, we had 131 different successful repairs for 60 different instances. This is because there is more than one repair for an instance. The experiments were partitioned to 3 sets according to the time it took for all repair to solve them. So here is the first set. This is the set for which the fast repairs were all repair. It took it to solve the instances below 5 seconds, and the dots along the x-axis are the instances, and the y-axis represents the time. We see here that there is no gain at all by adding the fault localization. On the other hand, when we go to medium repair, and more so when we examine the slow repair, then we get a significant gain. In the slow repair, note that the y-axis is now much larger than before. We see a significant gain by using the fault localization. Specifically, we have 6 instances which are timed out in the all repair. We see that they are on 3,600, which is the timeout of 10 minutes, while fault localization all repair was successful in coming up with repairs quite quickly. So to summarize, we suggested a novel masked fault localization with respect to a repair scheme. It is must and not may, meaning that you must change at least one of the lines returned. And even though the fault localization is must, its computation is relatively cheap. And our masked fault localization significantly speed up the mutation-based automated program repair tool, all repair, by pruning the search space without losing any of the good potential repair, without losing any good potential repair. Thank you.
Thank you, Arna, for the great talk. As always, like if you guys have any questions, just post on Slack or raise your hand here, and I can also unmute you. So one thing about, I guess, on program repair is that were this like one-line bugs, or there are also like multiple line bugs that you are targeting? Because I know that like
we can handle more than one bug.
oh,
Actually,
okay.
we don't have a limitation on the bug. In the experiments, we limited ourselves to 2 bugs at a run. It takes
I know that in the community of problem repair, right, multiple bugs fixing is much more challenging than the single bug, right, because of dependencies and so on, right. So you can guarantee then that the lines that you report will encapsulate both bugs. Then is what.
Yeah. This is not a problem. It's just since we try all kind of repairs, then it might increase significantly the number of cases that we have to consider.
Mm-hmm. But that's quite interesting as well. Yeah. And I know it's like of course you assume that you have a formal specification. Like in this case, either doing problem equivalence with the correct implementation, right, or some other sense, right. But doing problem equivalence can also be very expensive, right? If you're even with bottom wall checking, solving those formulas may not be easy, right? So I do notice some of these benchmarks tend to be kind of small. So if you wanted to scale up, would you use a different verification technique that would not be model checking, or maybe like the specification could be a bit more lightweight, or is that like a must? Because I guess without a formal guarantee, you will not have your must guarantee as well, right?
So if you use test suites to differentiate between good and bad runs, then there is a problem, a very known problem of overfitting, where the solution, the repair, is suitable for the set of runs that were given, but might be completely bogus for others. And the community that is using tests rather than specification is aware of it, and it's a problem that's hard to fix without any formal specification. And formal specification is more heavy. It's true also when we do verification as opposed to testing, we also pay a price.
No, but I do think this approach is quite interesting, and maybe it can complement each other, and it has different flavors, right?
Yes.
So I do think it's
thinking about using tests to speed up or to focus better the place to repair the site.
I imagine like if you have like a candidate that is given via test, then maybe you try then to pinpoint that one down and try to formally use the specification for that case, and could be a way to. Of course, you can't prove safety with this, but if you since you're just trying to find bugs, at least you can validate if it's a bug or not in a way. But I imagine there are some interesting combinations there. But I really like the must location set. I think it's a very nice idea, and I hope you continue to work on this direction. Okay, thank you, Ar. All right, so the last talk of the day is going to be by Martin Spiels. So he's a PhD student on his second year on the Institute for Informatics at LM Munich, and I'll give him talk about witness validation via verification.
Hello and welcome. My name is Martin Spiesel, and today I will present you some work I did together with Dirk Bayer at LMU Munich. I will talk about our approach witness validation via verification, which we implemented in our tool called MetaVal. First of all, let's have a look at the problem we want to solve. I'm sure everyone is familiar with the concept of a verifier. It takes as input a program and a specification, and it outputs true in case a proof has been found that the program fulfills the specification, and false in case a counterexample has been found, so there is a violation of the specification. Now, from a user's perspective, the verifier is like a black box, so why should they trust its results? One possible solution here is to output additional information in form of a witness. For a proof, we output a correctness witness that may contain important invariants, like a loop invariant. For a counterexample, we output a violation witness that may contain a way to limit the search space and point to the counterexample trace, something in the line of go left or right at a particular branching. This witness can then be checked by a validator. We can observe here that the validator is very similar to a verifier. Both take as input the program and the specification. The validator, however, has to additionally support and understand the witness format. This means that in practice we do not have a lot of tools that implement validation capabilities. If only we could just take a verifier and make a validator out of it. This is exactly what our approach does. Let's have a look at how it works. Our goal is to construct a validator by using a verifier. How can this be achieved? Our approach is that we take the original program, specification and witness and use a so-called transformer to generate a new program and a new specification that can then be verified by a standard verifier. The transformer is the crucial part here. We need to correctly turn the validation problem into a verification problem. So I will quickly explain how this works. Imagine we found a violation in a program for when we take the x bigger 0 branch in this small code snippet. A witness might add assumptions to a transition in the program in order to guide us. We can simply add those assumptions to the program. The witness might also indicate certain branches that do not need to be considered for the violation. Thus, we can just remove them from the program. In practice, it is a bit more complicated than that. We might also need to unwind the control flow, but I think you get the basic idea. Now what if we found a program to be correct? Imagine the verifier proved this by finding the loop invariant x bigger equals 0 for the loop in this small code snippet. The invariant is given to us in the witness. We now need to check that the invariant indeed holds, which can be done by asserting it every time we enter the loop head. In turn, we can assume that this invariant holds every time we leave the loop head. In practice, we might also need to unwind the control flow here, because the witness could specify that the invariant does not hold in every loop iteration. Now that we have seen how the transformation works, let's check whether our approach works in practice. We implemented our approach in a tool called MetaVal. MetaVal participated in the 2020 competition on software verification. We had to come up with a way of deciding which verifiers we would use for each specification. We stated the hypothesis that for each specification, the winning tool in the previous competition would also be a good choice for validation in that category. Here you can see the resulting mapping of specification to verifier. For reach safety, we use CPA-SEC. The best tool here was actually VeriUps, but because of license restrictions we had to use the second best tool. For overflows and termination, we use Ultimate Automizer. These two tools also have native support for validation, so the comparison with our results will be interesting. For memory safety, we use Symbiotic, which, thanks to our approach, can now for the first time be used in validation. Let's look at the results. This bar plot shows how many of the correctness witnesses for the reach safety specification each validator was able to confirm. We distinguish between uniquely confirmed, shown here in blue, which means that the validator was the only one that could confirm a particular witness, and non-uniquely confirmed, shown here in green, which means that at least one other validator was able to also confirm the witness. The numbers for our tool are comparable to those of the established validators. We were even able to confirm some witnesses that none of the other tools could confirm. For the specifications no overflows and memory safety, there exists only one other validator apart from our tool. Our tool adds alternatives here and thus helps in reducing the technology bias. For no overflows, we use Ultimate Automizer as verifier backend, so it is not surprising that the results are very similar. For memory safety, where we use Symbiotic, we even confirmed more witnesses than Ultimate Automizer. This indicates that our hypothesis that a good verifier will also lead to a good validation result cannot be completely wrong. These were the numbers for correctness witness validation. Now let's have a quick look at the violation witness validation. Here, there already exist more validators than for correctness witness validation. One reason for this is that violation witnesses can also be checked by executing the program directly, with the input values derived from the witness. This is done by the tools with witness to test in the name, which we abbreviated with W2T here. The results of our tool MetaVal for the no overflow specification, shown here, are comparable to the other validators. While for correctness witness validation we were almost as good as Ultimate Automizer, this is not quite the case here. This shows that our approach still adds some overhead, especially if the counterexample traces get longer. For memory safety, we are again very strong, because Symbiotic, the verifier we use, is very good in checking memory safety and can complement the other validators very well. The time is almost up, so what have we learned? We presented an approach that turns off-the-shelf verifiers into validators. Any existing standard verifier can be used as a verification backend. Implementation is a one-time effort. New verifiers can be used right away. New verification technologies can be instantly used for validation. Technology bias can be avoided by complementing the verifier by a validator that is based on a different technology. We showed that selecting the strongest verifiers can indeed lead to strong validators. If you are interested in more details, please have a look at our paper. Thank you very much for listening.
Thank you, Martin, for the great talk. I think
Thanks for having me.
Yeah, I think this is very important work. I mean, like, so in the Slack community, we also have like checkers that check solutions, and it's of course often the case that solvers were buggy in the past. So I think it's important to make sure that, especially tools that are doing model checking, output correct results, right?
Absolutely.
I do have a question though. So I think it's a really nice approach that it's very generic, and now you can transform any, I guess, verifier in a validator in some sense, right, with a transformation.
Mm-hmm.
But at the same time, like, let's say if the verifier is buggy, and then you use that verifier to check the witness, right? Couldn't it cause problems as well?
Yes, sure.
Yeah.
Of course.
So what would be your suggestion there, I guess? Yes.
So you can always compare different validators, of course. So you can use different verifiers. But also, you could also output another witness to check the result now of the validator. That's actually a common scheme, and you could cascade that down. But in the end, you will always have the problem that you can never be sure that all your verifiers are really free of bugs.
Yeah, you have to trust something at some point, right? I think like in the Slack community, how they did it was that they actually verified the validator with, let's say, Coq or Isabelle or some other language, just showing that, because usually the validator is doing something simpler. Of course, in this case, it's not, right? Because you actually just run the verification procedure as well.
And
but I think
there's actually another problem. So the transformation also has to be correct, right?
Exactly.
So it doesn't help here if the verifier we use is correct, but the transformation also could be buggy. And that could be hard to spot.
Did you verify the transformation, or do you have any plans?
No, there's no formal proof yet.
Okay.
Yeah, it's getting complicated, but we have a huge test set, so yeah. But there will always be bugs.
That's
sorry.
Maybe that would be like a first step, maybe like verifying the translation or the transformation, right? Since it's critical for the process. Another question I have, I guess we do have a question there on Slack. So Stefan asked, do you have any special issues arising for correctness weaknesses of parallel programs?
Of parallel programs, yes. So in theory, just take the invariants and input them. So we are kind of agnostic of the threading that goes on. So yeah. But of course, you could make use of special invariants that would be suited for multi-threaded programs, and we do not yet have had a deeper look into that.
So I guess this is the final question. So how much time actually takes to check the witness compared to verify it, right? Because often, I know that in stat solving a long time ago, it was more or less actually the same time, right? To check and verify. How is it nowadays in the SVComp competition?
So for violations, we take less time. So we only give a time limit of 90 seconds as opposed to 900, because the violation should be easy to track, right? Mm-hmm. But for the correctness, we actually give the same time as for verification, and sometimes the validation could even take more time. Ideally, if the invariant is good and if it really gives you clues, then you have less time, and you can show that you often can validate it in a shorter time. But in the worst case, of course, it could be the invariant is hard to prove for a specific verifier, and then it could even time out, of course.
Well, thank you anyway for all your answers, and I'll give a round of applause to all the speakers. Thank you very much for attending CAV. So this was like the last session, but we still have the breakout rooms. So I strongly encourage everyone to jump to the other Zoom link for a breakout room and talk with someone if you didn't talk with, and I think it's a really nice interaction in a virtual way. So we hope to see you all next year. Hopefully we'll be able to do it in presence, but I think there's also some good things about the virtual world, and maybe there's a hybrid approach for this that will make everyone happy. Well, anyway, thank you everyone again for joining us, and I'll see you next year.
Thank you.
Thanks.
Thank you.
Thank you.
Thank you very much.